In the first recording on the association between complex numbers and 2 by 2 matrices, we demonstrated that the number x plus jy could be equally well represented by the 2 by 2 matrix x, y, negative yx. We showed that when we do this, the multiplication of complex numbers works, and that the multiplication transfers to matrix multiplication of 2 by 2 matrices in the correct way. Here we will have a look at division and show that it also works. Let's consider the reciprocal 1 over x plus jy. Let's remind ourselves how we did that using complex numbers first of all. I hope you remember this. You basically take the complex conjugate of the denominator and multiply it on the top and the bottom in the way that I've shown here. The complex conjugate of x plus jy is x minus jy. So now we've got to expand out the product on the bottom. But that's not difficult, and in fact you may remember that it comes out to be real and positive. In fact we get x minus jy on the top still, and on the bottom x squared plus y squared. If we wanted to break that up, we could write it as x over x squared plus y squared minus jy over x squared plus y squared. Now, that was the reciprocal of the complex number x plus jy. 1 over it. We don't normally write 1 over a matrix, but instead we write the inverse of the matrix. So let's have a look at now the inverse of our matrix x, y minus yx. Do you remember how to do a 2 by 2 inverse? First of all we need the determinant. Let's call our matrix A or something. No, let's call it M. Okay, so we need the determinant. Determinant of M is just x squared minus y times negative y. That's x squared plus y squared. And then M inverse, remember, is 1 over the determinant. And then what we have to do is swap the two diagonals, but they're both the same, so they'll just still be x. And then we have to change the signs on the other terms. So minus y. That all looks very promising, doesn't it? X squared plus y squared underneath, well, yes, it is underneath in the reciprocal. And changing the signs of the off-diagonal terms, that's like changing j to minus j. It's a complex conjugate sort of operation. So sure enough, we get M inverse is x over x squared plus y squared minus y over x squared plus y squared, y over x squared plus y squared, and x over x squared plus y squared. And that is precisely the matrix which is associated with the complex number x over x squared plus y squared minus jy over x squared plus y squared. So we see that our analogy is useful for division as well. Let's do an example with some actual numbers, but now not a reciprocal, but actually one complex number divided by another. Suppose we want to look at, let's say, 2 plus j divided by 3 minus 2j. We would expect that to be equivalent to the complex number 2 plus j transfers to 2, 1, negative 1, 2, and 3 minus 2j transfers to 3 minus 2, 2, 3, but that's underneath, so we need the inverse for that matrix. Let's work out the inverse. We need 1 over the determinant. That's 9 plus 4. And we swap the 3's, but that leaves things the same, and change the sign on the 2's. So that's 1/13. 3, 2 minus 2, 3. And so we end up doing the matrix multiplication. 2, 1 minus 1, 2 multiplied by 1/13. 3, 2 minus 2, 3. And that comes out to be 1/13 can be put at the front, and we end up with the matrix. First of all, 6 minus 2 is 4, then 4 plus 3 is 7, minus 3 minus 4 is minus 7, and minus 2 plus 6 is 4, and we think that should be equivalent to the complex number 4 over 13 plus 7 over 13j. I will leave you to check using the usual method of complex number division that 2 plus j over 3 minus 2j is 4/13 plus 7/13j. In doing some of this arithmetic, we should have noticed something else that's quite interesting. That if z equals x squared, is x plus jy is represented by the matrix x, y minus yx, then if we call that matrix M, we have det M is x squared plus y squared, and that is the same as the modulus of z squared. So that's another feature of this analogy between complex numbers and 2 by 2 matrices that's of some interest and is quite important. I'm going to call it a day there.